Hello, everybody. I'm Ahmed Adaj, and I'm a system design leader on automated driving functions for Valeo. And I'll be presenting with my colleague Frédéric Bretagnol, Valeo part, which is the concept, optimization, and testing of sensors, cleaning functions under adverse weather. First, I will speak about the design of an automated driving supervision for an L3, L4 function to enhance end-user acceptance during fail-safe situations. Then my colleague will present Valeo cleaning and clearing sensor solution under adverse weather conditions. The main KPIs that were addressed during our proven of concept are the definition of a catalog of safety critical scenarios, mainly about adverse weather. Also, the implementation and demonstration of Valeo sensor cleaning technology. And finally, a proof of concepts of an automated driving supervision module. First, I will speak about mainly supervision and fallback. And to do so, let's have a look at the SAE automation levels table to first identify where is the borderline between human world and automation regarding dynamic driving task fallback. And here we can see that it's mainly located between level 3 and level 4 systems. This means that actually for fallback, driving is handing over the responsibility to automation to deal with it and to secure vehicle on any fail-safe situation. We can talk about different differences between the points of view between automation and driver, where we can see that driver, if he needs to handle fallback in his own, has the only options he has is, for example, here, mainly the hard shoulder on the right or the lane in front of him, and maybe also any additional information provided by the HMI. On the other hand, the automation can have a longer horizon where it can identify that there is a refuge area, for example, 2 kilometers away, and take the right decisions. Mainly, it's always about options and capacities, and about options, automation is clearly better than the driver. Here, we will try to emphasize the differences from fallback point of view, differences between the 3 levels of automation, L2, L3, and L4. For an L2 function, the driver is supposed to be monitoring the environment. So each time the system encounters a fail-safe situation, it's asked the driver to take back control immediately. And if he or she fails to do so, the system will deactivate right away. So, for example, the driver is just supposed to take back control on the steering and on the pedals. Some failure mitigation strategies coming from level 3 functions can also be implemented on L2. So for L3 function, the driver is not requested to be monitoring the environment, but is asked to take back control and maybe a longer time than L2, but in the end, he's supposed to take back control of the vehicle. If she doesn't fail, if she or he fails to take back control, the vehicle is supposed to implement a failure mitigation strategy where the vehicle can be stopped in lane, or maybe can be targeting a hard shoulder stop, but in a short horizon, which is not the case for L4 function, where the driver actually is completely disconnected from the environment and hands over the whole responsibility to the system. Where automation needs, on a fail-safe situation, will actually need to stop the vehicle safely in the best area. To identify this area and to planify the trip to reach it, the system needs to answer 4 questions that we will actually I will actually explain on this example. Let's take, for example, the solution of Cruise for You coming from Valeo that has many sensors implemented for highway use, for L3, L4 highway use. And let's take the assumption that we've lost the left rear sensors, or they are unavailable. There, we will first answer the question, where should I go, by identifying the road. So three lanes road with a hard shoulder and refuge area. Answering the second question, which is how long can I remain active, will actually put a limit to the operation, and will actually just reduce the option the automation has. On the other hand, we will answering what can I still do. For example, if I identify that there is maybe traffic on the right lane, the automation will say that the hard shoulder on the right lane won't be reachable. And on the other hand, as the left rear sensors are unavailable, the left lane won't be reachable also. So the answer to the last question, where can I go, is actually the stop in lane. On the other hand, maybe if we had an answer to the second question, which is maybe far away, taking the same assumptions on the left rear sensors, the solution might be changing lane 2 times till the refuge area. But what we need to know is that in this case, we targeted only stops in lane. So what if there were other options than stopping in lane actually, at the occurrence of a fail-safe situation? First, we will need to identify the 3 types of fail-safe situation, where we will need to deactivate on a system failure, on operational design domain limit, or on a vehicle failure. Let's focus on system failure, where we can identify some software failures or hardware failures. For software failures, let's take the sensor unavailability as an example, as it might be an event that can be reversible and that won't necessitate a stop in lane. So removing the cause to avoid a fail-safe situation will mainly increase system availability and enhance user acceptance. And actually, this is the aim of Valeo Sensors cleaning and clearing solution that will be presented by my colleague Frédéric right now. Thank you for your attention. Have a nice day.
Thank you, Ahmed, for this very nice introduction to our sensor cleaning part. I am Frédéric Bretagnol, and I'm working as project manager for sensor cleaning application at Valeo, and I will present you a short summary of the work performed in the frame of the Trust Vehicle program. So, as it was mentioned just before, one key point to maintain sensor availability and so frequency of fail-safe situation and so user acceptance is to maintain them clean and available under adverse weather. That could be just mud, snow, or rain, of course. In this part of the talk, we will focus our attention on the soling of the sensor and their cleaning. I will show you also a way to address the camera vision under rainy, snowy conditions, which are really particular conditions. To introduce more practically the topic, let me show you a classical situation that all the owners of a rear camera have encountered. You want to engage your reverse mode, but when you start at looking your screen to operate, you see nothing, because it's just simply full of mud. This is a common situation that you can have in winter season, of course, but also in summer season after a storm, for example. Fortunately, if your car is well equipped, you can use a sensor cleaning element allowing to realize the operation. Otherwise, it means that you have to get outside and clean it by yourself, or even worst of the worst, you can decide to not use any more of this function, whereas this camera is there to bring you comfort and safety. By this example of a simple application, you can understand easily why it's so important to ensure acceptance of self-driving function to maintain full availability of all the sensors that will be placed around the vehicle, and sensor cleaning is clearly fully part of the topic. So, in the frame of the project, we investigated this area by developing methods to apply soling and equipment to quantify accurately the soling level on the sensor surface in order to be able to optimize the cleaning function for both camera and LiDAR. In parallel, we investigate the importance to propose systems that can get rid of water droplets on the sensor surface. And finally, and it will be the main data presented today, we hit the road with fully equipped vehicle in order to test in real condition adverse weather situation. For that, as I was mentioning, we equipped the car with sensors. So here you can see the LiDAR and here the camera, what were placed at the front of the car. And they are optimized cleaning elements. So here you have the telescopic horn for the LiDAR, and here the cleaning element for the camera. We also use some specific tools that we developed in the lab in order to quantify the level of soiling on the sensors before and after cleaning. Then we went to the French Alps on several types of roads in order to meet several different conditions, and that are beautifully represented here, where you can find heavy rain situation, snowy conditions, semi-dry road, meaning just after the rain, and dry road, meaning a bit longer after the rain stopped. And just for illustration, here you can see very different patterns of sensor soiled after driving on the road, with snow, different type of muds for the different type of sensors. To go further, here you can see the LiDAR surface, which is fully blind after only 30 kilometers on snowy road, and on the side, the possibility which is offered by the cleaning element to remove the snow and to recover the sensor function within 1 second. Below, you can see the restoration of the video flow of a dirty camera at 110 kilometers per hour. What we noticed is that the worst soiling condition appears not under the rain, but more after in the semi or dry road conditions. You can also see that by using appropriate cleaning elements, you can recover the sensors in dynamic mode, but that the sensors are completely blind during the cleaning element, and that is a key point that needs to be considered for the final application. Here you can see the accumulated mud on a LiDAR after only 50 kilometers, meaning that the soiling of the surface can appear within a very short notice. Here you can observe the cleaning operation at 130 kilometers per hour, allowing to restore the initial surface state of the LiDAR. What is interesting to notice is that an important part of the distance of detection is lost after this 50 kilometers on semi-dry road, where some elements are not anymore seen after 80 meters. For example, this part or this part, when you compare the LiDAR sensor image before and after cleanings. Another important point to consider in the whole implementation of the sensor cleaning, as it was mentioned just before for the camera cleaning, is that the surface is completely blind during the cleaning operation, as you can see here, during the cleaning of the LiDAR surface, where all the information disappeared for a few seconds. This time is depending on the external condition corresponding to the time to evaporate the washing liquid on the surface, additionally to the cleaning time. So we have seen that the sensor can get dirty and need cleaning after rainy conditions. However, under rain, there is another pain point in the form of the water droplet on the surface that lead to important loss of information via distortion of the light. This is true for LiDAR and camera. Imagine the same story that I introduced at the beginning with the rear camera and the mud. So I will skip it and go straight to the point. To illustrate that it is possible to avoid this issue, we have used a system using a centrifugal force by placing a cover spinning around the camera, allowing to eliminate in a very short notice, few tenths of milliseconds, the water droplets. The advantage is that it can work from static situation, like reverse operation, but as you will see in continuous mode in dynamic situation, like on the road. On this image, you can see that without the system and under heavy rain, the image is strongly affected and cannot use in these states. However, when the system is active, you can see that the field of view is recovered, allowing to use the sensors as usual in safe condition. Other examples, under moderate rain or snow, where you can clearly see that some important glaring phenomenon can occur, and affecting in a great extent the vision quality and limiting the self-driving function. However, if you succeed to eliminate, for example, here with the centrifugal force, the water droplet, your sensor vision is maintained. I invite you in this way to follow the talk just after from Volvo, where they will show you interesting solution for LiDAR using air solution. To conclude, long story short, during this program, we highlight the importance of the sensor cleaning operation and parameters to consider and their optimization versus adverse weather conditions to reduce the frequency of fail-safe situation and so improve system reliability and user acceptance. It is also clear that to ensure the best self-driving experience, that sensor integrators and cleaning team have to work together in a really close mode to make it happen. So thank you for listening, and I will be more than happy to be able to answer your question at the end of the session. Thanks again.